Welcome to the next session, my dear friends. In the previous session, we were discussing about the alum reactions and what are the requirements of alkalinity for alum. What are the requirements of alkalinity for alum? See, alum Al2SO4 thrice, Al2SO4 thrice, 18H2O. When it reacts with bicarbonate, it gives 3CaSO4 plus 2AlOH thrice, 2AlOH thrice plus 6CO2 plus 18H2O. So we already discussed that 666 parts of alum needs 486 parts of alkalinity as CaHCO3 twice, and this 486 parts of alkalinity as CaHCO3 twice needs 300 parts of, or 300 units, whatever it may be, 300 parts of alkalinity as CaCO3, and this CaCO3 in turn needs 168 parts of CaO alkalinity. So now we can write the equations like this. So if 666 parts of alum needs 486 parts, then one part of alum needs 486 by 666 parts of alkalinity as CaHCO3 twice. Similarly, this one part of alum needs 300 by 666 parts of alkalinity as CaCO3. Similarly, this one part of alum needs 168 parts, 160 by 666 parts of alkalinity as CaO. Okay, alkalinity as CaO. Now x mg per liter of alum, x mg per liter, if the concentration of alum is x mg per liter of alum needs 486 by 666 into x mg per liter into 6x mg per liter of alkalinity as CaHCO3 twice, and 300 by 666 into x mg per liter of alkalinity as CaCO3, and 168 by 666 into x parts of alkalinity as CaO. So these are the requirements. That means when you are adding x mg per liter of alum to water, when we are adding x mg per liter of alum to water, in that water there should be alkalinity of 486 by 666 into x mg per liter in terms of CaHCO3 twice. If this much is not there, how much is present, that we will leave, and the rest additional extra we need to add it externally, okay, in the form of CaHCO3 twice. Or if you want to add it in the form of CaCO3, then for x mg per liter of alum needs 300 by 666 into x mg per liter of alkalinity in the terms of CaCO3. Similarly, if we are adding it in the form of a lime, then it should be equal to 168 by 666 into x parts of alkalinity you need to add to the water in terms of quicklime. Okay, these are the requirements. These are the requirements of alum, for the alkalinity requirement of the alum. Similarly, actually this is how we adding the calcium bicarbonate, calcium carbonate and the quicklime. If we are adding something else, if you are adding lime directly, hydrated lime, then how the reaction will be? You are adding hydrated lime, for example, if we are adding hydrated lime to this, then what is the reaction? Al2SO4 thrice 18H2O plus CaOH twice 3 CaOH twice, it will give you 3 CaSO4 plus 2 AlOH twice, OH thrice plus 18H2O plus 18H2O. So this is the reaction when we add lime. Similarly, we can add soda ash, that means sodium carbonate. We can also add soda ash to this. That means if you are adding soda ash, that is also alkalinity. If you are adding soda ash, this is soda ash, sodium carbonate, soda ash, then it will form Na2SO4 plus 2AlOH thrice plus 3CO2 plus 15H2O. So here this is the reactant. This is the reactant. Now if you look at these reactions, now we have studied about the reactants so far. So far what we have discussed is what is this concentration, what is this concentration. So we have discussed about the reactants. We haven't seen the products. Now let us see the products and derive some kind of conclusions from the products. See, similarly how we have derived this 666 units is equal to 486, similarly for these also we can do, but for examination these equations are not that important. This equation is predominantly used, so that is why I am only using this equation for the explanation of the requirement of alkalinity. Majority of the questions in the examination that will come from this equation only. These equations, what is important is the reactants, the products. So what are the products that are coming out of these three reactions? We can establish a comparison. That is why these equations are important. If you look at the if you look at the first and second equation, when alkalinity is provided in the form of bicarbonate, of calcium and hydrated lime, bicarbonate of calcium means what? Bicarbonate of calcium means CaHCO3 twice. So when you are adding alkalinity either in the form of CaHCO3 twice or in the form of CaOH twice, it imparts permanent hardness to water. It imparts permanent hardness to water because here CaSO4 is coming. In these two reactions, if you see, the CaSO4 is coming, that means the alkalinity, if it is provided in the form of CaHCO3 twice and CaOH twice, then it will impart permanent hardness to the water, that is CaSO4 is coming. Okay. Next is when alkalinity is provided in the form of CaHCO3 twice and Na2CO3, it causes acidity to the water. It causes acidity to water, or it imparts acidity to water. It imparts acidity because here see COT is coming, here COT is coming. In these both reactions COT is coming, that means this CO2 will form into carbonic acid, so it imparts acidity. Which causes corrosiveness of the materials. Okay, it imparts acidity because of the presence of the CO2 in both the reactions. So here generally we use alum. This alum as a universally adapted coagulant because it is easy to procure, because it is easy to procure, as it is cheaper and storage is easy to store and very cheap to procure. And here it works in a pH range of the alum is cheap, economical, and easy to store, and it works in a pH range of 6.5 to 8.5. 6.5 to 8.5, which is the pH range of water, which is the pH range of drinking water. That is why So alum is generally fit for treating the drinking water, that is raw water which is fit for drinking. So this is the this is some kind of points which are important in terms of alum and its reactions. Okay, now next is, so how to find this alum dosage. That means if there is impurity, so if there is impurity in the lime, for example, if there is impurity in the lime, then generally we need to procure more lime, that I will explain. And also one more point that is important is, sometimes in the examinations they may ask, they don't ask you the alkalinity, they don't ask you the requirement of alkalinity, they will ask you how much carbon dioxide is evolving out of this reaction. So for this much dosage of alum, how much is the carbon dioxide is evolving? So that is also important. One part of alum creates how much of flock, and one part of alum creates how much of carbon dioxide. That is also sometimes they may ask. So we need to derive a relationship for them also. After that I will explain if there is impurity and all, what needs to be done, that I will tell you. Here 666 parts of alum, 666 parts of alum develops the molecular weight of this ALOH thrice is, the molecular weight of ALOH thrice is 78 is the molecular weight. So 78 into 2, 78 into 2, that is 156. That is 156. 78, 156. So 156 is the molecular weight of this. And this carbon is 12 plus 16, 18. 18 is 1 unit, 1 mole of carbon dioxide weighs 1 mole of carbon dioxide weighs how much? 12 plus 16, 32, 12 plus 32. This is 16 to the 32 and this is 12. 32 plus 12, 44. 6 into 44. Here it is 6 into 44, whereas here it is 3 into 44. So depending upon the reactant, depending upon the type of alkalinity we provide, the value of carbon dioxide which is coming is varying. Okay, so 666 parts of alum develops 156 parts of flock when alkalinity is provided. Say anything, any alkalinity, the same value, 2ALOH thrice, 2ALOH thrice, 2ALOH thrice. So there is no need of terming alkalinity, because whatever be the alkalinity, it is constant value. So that it is not needed to write which kind of alkalinity we are providing, because for all the kinds of alkalinity it is 156 parts only. So now one part of alum develops 156 by 666 parts of flock, and x mg per liter of alum develops 156 by 666 into x mg per liter of alum of flock. Okay, so this is flock. Similarly, so when it is CaHCO3 twice, so when CaHCO3 twice, alkalinity, when CaHCO3 twice alkalinity is provided, then 666 parts of alkalinity, 666 parts of alkalinity, 666 parts of alum generates 6 into 44 parts of 6 into 44 parts of CO2. Okay, so similarly we can write it for Na2CO3 also. When Na2CO3 alkalinity is provided, then 666 parts of alum gives 3 into 44 parts of CO2. See, generally in GATE examination, sometimes they don't ask conventional questions. They go completely away from the conventional questions. So they will ask some different kinds of questions. In that scenario, these kind of things are important. Generally in regular pattern, these kind of relations may not be important. But if they want to go away from the conventional pattern, they want to ask something new, then these are the locations where there is a possibility to ask something new, because every time they will ask the alkalinity requirement. Every time they will ask what is the alkalinity requirement. If they want to change the type of questions, then they may move on to the products. So every time they are asking on reactants only. So that is why sometimes products are also important. So that is why I am explaining all these things. This is not important for regular pattern, but if they want to ask something new, then these kind of questions are very, very possible for asking. Okay. Now here everywhere we are saying that x mg per alum, x mg per alum, x mg per alum, everywhere we are saying that these 666 parts needs this much parts, one part needs that much parts. For x mg per liter of alum, we are writing everywhere. What is that x? What is that x? How to define that x value? How to define that x value? How to define that x value? That x value, generally we define x is nothing but the optimum dosage of alum. X is nothing but the optimum dosage of alum. So that is defined, it is determined by using jar test. That is determined using the jar test. And in the previous explanation I was telling that if you are taking a quicklime, then quicklime will have some purity. Sometimes quicklime may not be 100% pure. If you are providing alkalinity, okay, if you are providing alkalinity by any means, so that particle, that material, whichever we are using for giving alkalinity from external side, may not be 100% pure. It may be some 80% or 85% pure. Then in order to take care of the impurities, we need to add extra. That means 80, if you are taking a quicklime, for example, take quicklime. So that quicklime, it was told that it is 80% only pure. It is 80% pure. That means if you take 100 kg of quicklime, there will be only 80 kg you will get. 20 kg is not quicklime. It is some kind of impurity present in it. So in that case, if you add 100 kg, you will get only 80 kg. So during the procurement of alkalinity, in the form of quicklime, it is CaO. So let us assume that it is 80% pure. It is 80% pure. Then for every 100 kg of For every 100 kg of quicklime, for every 100 kg of quicklime, we get only 80 kg useful. Right. So that means if you want 100 kg to come, so if the requirement is 100 kg, then if you add 100 kg, then you will get 80 kg only. That means if you want 100 kg, you need to add something extra, right? So for getting 100 kg, so you need to add something extra. So let that extra is y. So if this is the quantity you are adding, and in this quantity only 80% is pure. So that means 0.8 times into this quantity should be equal to 100. Right? 0.8 times of this quantity should be equal to 100. That means y is equal to 100 by 0.8. Right? So if 100 is the requirement, so if the requirement is something x, then we need to take y amount such that it will give x. Okay, such that it will give x. So y is the amount needs to be procured. So here y is amount of quicklime, amount of quicklime to be procured. X is the amount of quicklime present or the demand. Amount of quicklime present or demand of water. So this is the requirement. To meet this requirement, you need to procure this much, because in this only some percentage is pure, rest of them is impurity. So that is why, so y is the amount I need to procure. So in that amount only, for example, if it is 80% pure, then it is 0.8 times of the amount procured. It is the fresh lime, the pure lime is 0.8 times of the procurement. That is equal to x is the requirement. This is requirement. And this is procurement. So procurement should be higher, as because in the procurement there is some impurities there, but the requirement is the exact necessary. This much it should be 100% pure. This is requirement. This is procurement. That is the difference. If it is impure by 80%, then the factor is 0.8. If it is 85%, the factor is 0.85. If it is 90%, the factor is 0.9. Whatever the purity it was given, similarly the factor will changes. Am I clear? So this is what I was telling. It may be quicklime, it may be hydrated lime, it may be bicarbonate, whatever it may be. So if it is impure, then we need to take something extra. Okay. So now, finding the optimum dosage of alum. So let us discuss briefly about jar test. So in jar test, generally we take 4 jars, and each jar we take the alum at different dosages. It is used to estimate the optimum dosage of alum. The optimum is used to estimate the optimum dosage of alum. See here, we take 4 jars. In this jar there will be paddles. So we take 4 jars like this. In this we take water, raw water into this jar. Raw water, we will pour the raw water for which you want to do this treatment and all. So all the raw water will be taken from the same source. So in this I will add alum 10 mg per liter. We will add alum 10 mg per liter concentration. Here in this we will add an alum of 15 mg per liter concentration. Here we will add alum of 20 mg per liter concentration. Here we will add alum of 25 mg per liter concentration. Okay, here we will add it like this. If you see the turbidity versus alum doses, turbidity versus alum doses chart. So this is turbidity, because alum reduces what? Turbidity only, and alum. So at the low doses, the turbidity may be more. When you increase the dose, so turbidity reduces. Okay. Further, if you increase the dose, turbidity has further reduced. Further, if you increase the dose, turbidity has increased again. So this is the chart of alum doses versus turbidity. Alum doses versus turbidity. So earlier, to some extent, the alum doses may vary. To some extent, the turbidity may reduce. But what happens if you keep on increasing the alum doses? If you keep on increasing the alum doses, the turbidity again increases, because the alum now beyond this point, alum is not required. Up to this point, alum is required. Here at this point, all the turbidity has got settled by this dosage of alum. Further, whatever the alum you are adding, it will become again turbidity. That means whatever the alum you are adding, because there is no colloidal particles to settle down, so all the colloidal particles are over. Now whatever the alum you are adding, it will behave like a turbidity and it enhances the turbidity. That means if you add more alum doses, that alum itself becomes turbidity again. So that is why it is necessary to add alum as per the requirement. That is called optimum dosage of alum. So this jar test, using this jar test, we will plot the turbidities of different concentration, what is the turbidity and all. So if you connect it, then you will get the least point of that graph, that is called where you are getting the least turbidity, that corresponding dosage of alum is called optimum dosage of alum. Okay, that corresponding dosage is called optimum dosage of alum. That is why we use this jar test. Okay, so now after this jar test, so there are some more coagulants. I have told you, apart from the filter alum, there is copperas, chlorinated copperas. So those reactions and about them briefly we will discuss, because majorly the questions may come from filter alum. Majorly, very few instances there is a possibility to get questions from the copperas, chlorinated copperas and all. So that is we will discuss in brief. Okay, not in detail, in brief about this iron flux, the coagulants which are having iron in it. So first one is copperas or hydrated ferrous sulfate. hydrated ferrous sulfate FeSO4 7H2O. FeSO4 7H2O. So when this FeSO4, when it reacts with alkalinity, FeSO4 7H2O, when it reacts with alkalinity CaHCO3 twice, then it will give FeHCO3 twice. It will give FeHCO3 twice, plus a CaSO4 plus 7H2O plus CaSO4 plus 7H2O. Again, this FeHCO3 twice, it will react with hydrated lime, FeHCO3 twice, reacts with hydrated lime, and it forms FeOH twice, this is the flock, FeOH twice, this is plus 2 CaCO3 plus 2H2O, this is not flock, 2 CaCO3 plus 2H2O, 2 CaCO3 plus 2H2O. Again this FeOH twice reacts with oxygen and CO2 in the presence of H2O, in the presence of H2O, it forms FeOH thrice plus precipitate. So this is flock. This is the flock. So this much of reaction is not needed to remember. If we add directly CaOH twice to this ferrous sulfate, if you add directly CaOH twice, then FeSO4 7H2O plus CaOH twice, then this equation will form. We can directly add, that means the same equations will come here also again. It is not needed to write. If you add bicarbonate, then second step we need to add a hydrated lime also. For this bicarbonate we need to add a hydrated lime also. If you are adding directly the hydrated lime, then it is not needed to write this equation. These two equations will come. If either we can add directly hydrated lime or you can add directly bicarbonate. If you are adding bicarbonate in the second step, hydrated lime in the third step, you need to add oxygen and H2O. So this much of equations remembering is not that easy. Okay, so that is why generally this is not that important for the examination. If they are asking this in examination, they will provide you with an equation of directly. So these two relations, okay, they may ask you what is the alkalinity requirement. So it is not needed what is the reactants. Alkalinity requirement you can say by looking at the reactants. We have no need of looking at the products. So if you are seeing reactants, so for this much of alum, for this much of copperus, this much of alkalinity is needed in the form of bicarbonate. For this much of alum, this much of the ferrous sulfate, this much of lime is needed. If you add this also, directly CaOH twice if you add, that means here the reaction will start. So FeSO4 7H2O plus 2 CaOH twice. So from here the reaction will start if you are adding directly CaOH twice. So now it will form CaSO4. It will form CaSO4 plus FeOH twice. CaSO4 plus FeOH twice plus 7H2O plus a 7H2O. So this is the reaction when you add directly CaOH twice, and the third next once it came, then this reaction follows this reaction also. The same reaction will come here also. So that is why this is not that important. Reactions are also not important. If anything asked in the GATE examination, they will directly provide you the reaction along with the atomic weights also. It is not needed to remember the atomic weights of iron, sulfur, oxygen and all. They will provide you that also. Okay. So that is why just knowing the reactions is sufficient. No need to think much about it. But the concept you know. So this many parts to this many parts, the comparison and all you know. So what we have did in alum, the same concept you will apply here. Only thing is, in alum we have taken the molecular weight of alum. Here we are taking the molecular weight of copper. That is the only difference. Okay, rest is same. The concept is same. Second one is chlorinated copperas. Let us see the reactions of chlorinated copperas. Next is chlorinated copperas. See, chlorinated copperas is when this alum is reacted with chlorine. The alum is reacted with 3FeSO4 7H2O when it is reacted with Cl2. When it is reacted with 3Cl2, then it will form 3Fe2 Fe2SO4 thrice, Fe2SO4 thrice plus 2FeCl3, 2FeCl3 plus 7H2, 21H2O. Here 21H2O. This is the first reaction. First we will add chlorine to the copperas. That is called chlorinated copperas. This ferric sulfate and ferric chloride combinedly called, these two combinedly called chlorinated copperas. So this is ferric sulfate and ferrous chloride, ferric chloride. So these two combinedly called chlorinated copperas. And next, this ferric sulfate Fe2SO4 thrice. So this will react with hydrated lime 3CaOH twice, and it forms 3CaSO4 2FeOH thrice. 3CaSO4 plus 2FeOH thrice. This is the precipitate. Similarly, here this ferric chloride also reacts with lime. And it also forms 3CaCl2 plus 2FeOH thrice. This is the precipitate. This is the flock. See, this is nothing but flock. Okay, FeOH thrice is the flock. So these are the reactions for chlorinated copperas. These are the reactions for chlorinated copperas. Nothing much important in this. So only reactions from there. What is chlorinated copperas and all these things may be needed for the examination. Not that important, may be needed. So next is sodium aluminate. So we are left with one more coagulant, that is sodium aluminate and lime. These two we will discuss in the next class, and we will discuss about this mixing of this. That means how to mix the alum, and what is the comparison between the iron flock and aluminum flock. And I told you different mechanisms will happen, different locations. Those things all we will discuss in the next session. Thank you so much.